Good afternoon, students. Welcome to EBS 357, Introduction to Atomic Physics, Heat and Optics. In the last lecture, we tried to look at the history of the atom and the atomic models that, came up right from one of the renowned scientists, which we describe as Nucleus, who actually did not back his model of the atom with any experimental evidence. We also looked at what Proust proposed as a model of the atom and saw in the discussion that he proposed a law which we describe as the law of definite proportion or constant proportion. Today, we want to continue with the history of the atom. The objectives for today's lesson includes, we're going to state the postulates of John Dalton. We also identify the negatives of John Dalton's postulates. Again, we'll be looking at what J.J. Thomson did by way of experiment in his discovery of the electron, and then some of the findings that he actually came up with. We'll also look at Ernest Rutherford's experiment and conclusions drawn from thereof. Now let's start with John Dalton. John Dalton reigned between 1766 and 1844. The date 1844 rings bell in our minds if we talk of the born of 1844 and all those things. It means John Dalton reigned from 1766 to 1844. And this is the man we want to talk about. He was a meteorologist. Okay? Dalton was a meteorologist. And unlike Democritus, he had experimental evidence to support his theory about the atom. That's how come in the slide that contained all the renowned scientists who have contributed to the model of the atom, John Dalton's name was amongst of those scientists, and he actually came first. Dalton actually did a lot of experiments using gases, and in his experiments came up with 4 major points which we describe as postulates. So you think of Dalton's postulates or Dalton's theory. Now we take the theory or the postulates one after the other. It was Dalton who said that all elements are composed of indivisible particles called atoms. So you see the word indivisible has come again. So up to the time of Dalton, people still believed that the atom was indivisible particle. That is, it could not be split into smaller entities. We would soon find out from you what lapses you think this postulate has with the modern model of the atom. The second postulate, according to Dalton, it says atoms of the same element are identical. The atoms of any other element are different from those of another. Again, you should be looking at this definition or postulate and be comparing that with the modern model of the atom. By the time we are through with the fourth postulate, I'll be asking you to tell me what lapses you detect in Dalton's theory. Let's go to postulate number 3. Dalton also says that atoms of different elements mix or combine in whole numbers or ratios. Example, oxygen combines with hydrogen to form water in a ratio of 2:1. Now, of course, you would agree with me that this idea came from Proust. And this is what Proust actually described as the law of constant proportion. So, Dalton also saw that this proposition is actually making sense, hence he postulated. His fourth postulate says that chemical reactions occur when atoms separate, join, or rearrange. And we also saw this in Proust's experiment. Thus, we have water being formed as a result of a combination of hydrogen and oxygen atoms. At the same time, if you want to form sodium chloride as the salt or the table salt that we all eat, you realize that you need some sodium atom and chlorine atom to combine. So that means that the atoms in there join. They join to form the compounds that I've mentioned. That's water and sodium chloride. In the same vein, you could get the sodium chloride separating into its entities, having the sodium and then the chlorine. So in that case, we say they will separate to form a new substance, and that's what Dalton described in his fourth postulate. Now let's make progress and look at the side notes, okay, which we would consider, okay, as not correct or something that did not go down well with modern atomic theory. Today we know that atoms are indeed divisible, right? Because we know that when we split the atom into its elementary particles, we may end up getting protons, neutrons, electrons, and we even said that these particles can still be split into other smaller substances like the muons, the quarks, and so on and so forth. So again, Dalton's postulates did not consider this very important observation. The second issue has to do with the fact that we said there are isotopes, okay? And we defined isotopes as atoms of the same element having the same number of protons but different number of neutrons, hence different atomic masses. And so the examples that we give include the fact that carbon can exist as carbon-12, can also exist as carbon-13, we can have carbon-14. In carbon-12, there are 6 protons and 6 neutrons, okay? Carbon-13 will have 6 protons but 7 neutrons, making it heavier than carbon-12. The same will go for carbon-14, probably having 8 neutrons and 6 protons. So that depending on where you find your atom, okay, it might be of the same element but may come with a different mass. And this is one thing that Dalton did not consider in his postulates. So one may say that those were his lapses. The fact that one, atoms can be divisible, okay, to get protons, neutrons, and electrons. And those protons, neutrons, and electrons can further be divisible to get the muons, the quarks, and then the rest. And at the same time, we're also saying that atoms could come in different forms, but from the same element. Now let's move on to J.J. Thomson. J.J. Thomson is also associated with the Plum pudding model of the atom. But let's find out how this name Plum pudding, and also the fact that he is the one who discovered the electron. Let's see how this came about. So this is the man in your short, J.J. Thomson. Perhaps you have to go and find out what the J and then J means, so that at least when you want to talk to somebody about him, you will be in a position to mention his full name. There's an assignment I'll ask of you. He actually did his experiment using the cathode ray tube. So you normally will hear the cathode ray tube experiment by J.J. Thomson from 1859 to 1940. In your shot is the cathode ray tube. This is common when you open the old televisions. You see a certain tube behind it, and that is what we may be referring to as the cathode ray tube. The advanced ones today, but that is what he used. In the tube, he actually put some inert gases so he could study the gases, the behavior of the gases. The tube contained 2 plates, a positive and a negative plate. Now we all know what inert gases are, so I want you to just pen down some few examples of the inert gases. Yeah, I believe you have been able to pen down few of them. And so let's go through the list and see if what I'm going to mention, happens to be in your list. So helium is an inert gas. Neon is an inert gas. We have radon. We have xenon. We have krypton. And these, I believe, you have them on your papers. So he picked either of these inert gases and placed it in the cathode ray tube. We are saying that the cathode ray tube contains 2 plates, a positive and a negative. Now he saw that the particles in the gas were attracted to the positive plate. When J.J. Thomson put the inert gas, which is supposed to be unreactive and will not interact with any other material, chemically, J.J. Thomson saw that the gas particles, some of them were attracted to the positive plates of his cathode ray tube. Now, you should be thinking about what this probably would, be the reason for which the gases were attracted to the positive plates. Now, ideally, when we take the first law of magnetism, okay, we see like poles repel, unlike poles attract. When you go into electricity, you also find there like charges repel, unlike charges attract. So basically, if you get some particles being attracted to positive, particles or a positive plate, then one would have, assumed that those particles will probably be negative in nature, because we said like charges repel, unlike charges. So positive and negative would attract. So if you get those particles from the gas being attracted to the positive plate, then it means that those particles are negative, and that's exactly what J.J. Thomson discovered. So this is the experimental setup of J.J. Thomson's experiment. You see in your shot the cathode ray tube having two plates colored yellow and blue. So the yellow on top and then the blue is down. And you also have some magnets, the north and south poles inside this, just to paint the picture of what I earlier on talked about. And so the red thing you see passing through the cathode and then the anode is supposed to be a gas that's J.J. Thomson used, the inert gas. So passing through the two plates, you see that some of the red lines, if we should put it that way, move towards the negative plate and some move towards the positive plate. Others went straight. Yes. The observation that was made by Thomson was that most of the particles were attracted to the positive plate. And so we have indeed concluded that the particles are supposed to be negative in nature. We would have to watch a video on this so that we'll get a clear picture of what J.J. Thomson did. So let's go and watch the video and come back.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence, or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Yeah, I believe we have all watched the video of J.J. Thomson's experiments. And so I'm going to ask you some few questions so to check if you followed the video as was played. Now the first question is that we saw that the inert gas was going through the two plates, okay, the path where the two plates would have been were going through, and there was no form of deflection. When the plates were brought, to which direction did the inert gas move? Good. So I believe you all saw that it moved towards the positive plate. Now this time round, the positive plate was replaced with the south pole of a magnet. And we saw that the gas particles moved away from the south pole. When the north pole was brought, the gas particles then came back, getting attracted to the north pole. And so basically we may even say that the north pole is likened to the positive plate, and then the south pole likened to the negative plate. So in short, the gas particles were attracted towards either the north pole or the positive plates, indicating that the particles would be negative in nature. So now let's see what J.J. Thomson concluded in this experiment. He actually said those particles were electrons. So we can see that J.J. Thomson discovered the electron. I hope that is clear. Yes. Now from his experimental evidence, he believed that the atom was a solid positive sphere with electrons shoved into the sides of it. Okay? J.J. Thomson actually said his model resembled a popular English dessert called plum pudding, and so called because he actually, showed how the plum pudding looks like, and you can see this in your shot. In Ghana here we may be calling this one as a pizza sort of, So you see the black things inside the pudding is actually representing the electrons, whilst the entire thing is actually the atom with some positive charges inside it. So J.J. Thomson's model of the atom is called the plum pudding model. The plum pudding model. Remember, we are saying that J.J. Thomson discovered the electron. We would soon find the mass to charge ratio of the experiments that we did. But let's make progress. The next scientist on the roll is Ernest Rutherford. Ernest Rutherford, 1911. This man also performed series of experiments, but decided to use the gold foil, fire some alpha particles through it to find out what will come out of it. At the time, experiments were just common. Everybody would wake up and say, no, let me find out if this is that. Maybe what J. Thompson has done is correct or wrong. So people were just, doing, all sort of experiments. So Ernest Rutherford used the gold foil experiment to discover the nucleus of the atom. Let's find out how this was done. Rutherford shot high energy beam of alpha particles into a gold foil. Now, from your lesson in radioactivity, that's the disintegration of radioactive material, which leads to the formation of or release of alpha, gamma, and beta particles or radiations. We learned that alpha particles are positive in nature. Okay? So Ernest Rutherford actually fired those positive alpha particles through the gold foil and wanted to find out what will come out of it. Now on your screen, you can see that the alpha particle actually went through the gold foil, and there were about 3 discoveries. 3. Because some of the particles went through, others got deflected at greater angles, and others got deflected at smaller angles. We would have to look at the experiment in video so that we'll be able to give good account of what actually went on. So let's watch the video by Ernest Rutherford. Yes, audio. Yeah, so I believe you all watched the video keenly and you've taken notice of the things that went on in that video. Now, on your short, or in your short, you find the experimental setup, gold foil experiment. There is a box which actually harbored the alpha particles coming from lead or any radioactive material like uranium and so on and so forth. So the radiation this time came from radium and went through the gold foil, and you can see the red light. Some got penetrated through the gold foil, others got reflected, and others got, deflected. So, I mean, there are three observations there which we want to look at and also make conclusions or draw conclusions from that. The first observation that Rutherford made was that most of the alpha particles went through the gold foil. Okay? Secondly, he saw that few particles were deflected at small angles. Thirdly, very rarely particles were deflected at large angles. And with all this, let's look at the conclusions that he drew from the observation. So the first one, because he saw that most of the alpha particles went through the gold foil, then he said the atom is mostly empty space. Okay? Because if you have all the alpha particles just going through, then it means there's no obstacle there. So that means that the atom is actually an empty space. Now, few particles were deflected at small angles. Let's see the conclusion. The conclusion is that the alpha particles came close to something small and positive, probably the nucleus. Okay? Something small and positive. And there will be deflection. Deflection because, one, you hit the thing, and you, the alpha particle yourself, you are positive. The nucleus is also positive. So if the two of you collide, one would have to go away. And so the deflection of those few particles, can be seen to be because the nucleus is there, those alpha particles could not go through it, yet they deflected because the alpha particles themselves are positive in nature. The third observation, very rarely particles were deflected at large angles, and this conclusion was also made by Ernest Rutherford, that the alpha particles hit a small, very dense and positively charged center, again, which we can call the nucleus. And so by this experiment, I expect everyone to be able to, one, go through the experiment by way of, describing what happened, the observations that were made, and the conclusions drawn thereof. Now, it is worth noting that some other scientists actually made some gains between the era of consideration. So a man like Eugene Goldstein, 1850 to 1930, also is thought of to have discovered the proton. Now, you are supposed to do research into this, find out what Eugene Goldstein did and how he was able to discover the proton. Another man, James Chadwick, 1891 to 1974, also discovered the neutron. Chadwick discovered the neutron. So, as a research, please find out how these two individuals were able to discover the proton and the neutron. Now that we know and we are aware that the atom is made up of some particles We will now look at these particles and indicate where they can be found in the atom. So we also look at their properties, because already J. Thomson has told us that the electron is negative in nature. So particles, symbol, charge, and its relative mass. Now we take the proton, as has already been said. The symbol is P and has a charge of positive 1.6 times 10 to the power 19 coulombs. In your basic school science, they tell you the charge of the proton is +1. But we have grown past that. And so the charge on the proton is actually 1.6 times 10 to the power 19 coulombs. The relative mass is 1. Relative mass of the proton is 1. Neutron is also located in the nucleus of the atom, just like the proton, and it symbolizes N. It has no charge. So when we put 0 there, 0 implies no charge. So, I mean, it's better you even write neutral, okay? And then we know that it also has a mass of 1. Then the last one, which is the electron, they symbolize E with a negative on it and has a charge that is opposite to that of the proton, and so that will be minus 1.6 times 10 to the power 19 coulombs. Okay? So, yeah, I can see most of you discussing the issue of the electrical neutrality of the atom. And it is true, because the proton balances the electrons. And if you look at their charges, plus 1.6 times 10 to the power 19 coulombs and negative 1.6 times 10 to the power minus 19 coulombs, then they balance. So if I have an atom with 6 protons and 6 electrons, that atom becomes electrically neutral. The charge of the electron is opposite to the charge of the proton. Now, if you look at the mass of the electron, then we can see it is 1 out of 1840. Okay? 1 out of the 1840. So, if you want to find the mass of the electron, you actually divide 1 by 1,840 of the proton, and you get that. So, like I said, we want to find the location of these particles in the atom. So, protons are in the nucleus, as we have said already. We also want to say that neutrons are in the nucleus. Then, the electrons are actually in what we call electron cloud outside the nucleus, and this specifically we call the energy levels, or the shells, or the orbitals. Any of these is correct. So we talked about the neutral atom as having equal number of protons and electrons. An atom is considered neutral when it has the same number of electrons and protons. Now, you will take this as an assignment and present this in our next lecture. You are supposed to be looking at the shortcomings of the different models of the atoms that have been proposed by the various scientists whose names we have mentioned, and do that kind of comparison. Also, what are the drawbacks of the Rutherford model of the atom, okay? It's the same as shortcomings anyway. I want to find out the limitations of J.J. Thomson's, model of the atom. In our next lesson, we will be looking at the Bohr model of the atom and discuss the Bohr radius. In fact, inside this lesson, we'll also be looking at the hydrogen spectrum and then the spectral lines or spectral, series. Thank you very much for your attention, and I want to say thank you to the cameraman and the technicians who have yes, and again we want to say thank you to this technician who put this wonderful work together. We want you to subscribe to the YouTube videos and then like them as well. Thank you so much. And please, COVID-19 is real. COVID-19 is real. So we want you to go by all the safety protocols because we want you back in one piece and not in pieces. Bye for now.